Imagine pouring more than $100 million and the hopes of an entire generation of climate scientists into a single, silvery object hurtling above our heads. Imagine years of meticulous research and global collaboration, all focused on a satellite that was supposed to change the way humanity tracks one of the most dangerous greenhouse gases on the planet. Now imagine watching that dream flicker out, all within a little over a year. This is the story of MethaneSAT, a satellite whose mission was to transform the fight against climate change, and whose sudden failure in orbit has sent shockwaves through the worlds of science, policy, and technology. As we lose one of our brightest eyes in the sky, we are forced to confront some uncomfortable questions. How do we track invisible pollution when our best tool goes dark? What does this mean for the future of global methane accountability? And can technology really save us from ourselves? Or are we placing too much faith in fragile machines? For decades, the world's ability to track methane leaks has been patchy at best. Ground-based sensors and periodic flyovers can only catch so much. Most emissions, especially from remote oil and gas facilities, agricultural sites, and landfills, go unnoticed. Enter MethaneSAT, a privately funded, technologically advanced satellite that promised to pull back the curtain on this hidden pollution. Backed by the Environmental Defense Fund, with support from high-profile individuals like Jeff Bezos and governments like New Zealand, MethaneSAT was not just another satellite. It was a symbol of a new era, one where civil society, technology entrepreneurs, and scientists worked together to hold polluters accountable on a planetary scale. MethaneSAT's mission was ambitious from the start. Its goal was to deliver unprecedented high-resolution data on methane emissions from oil and gas facilities all over the world. By combining sweeping global coverage with the ability to zoom in on hotspots, MethaneSAT could detect methane leaks as minuscule as 2 parts per billion, a sensitivity unmatched by most other platforms. This meant that scientists, regulators, and the public could, for the first time, pinpoint exactly where emissions were occurring, track the effectiveness of repairs, and shine a light on polluters who might otherwise operate in the shadows. The stakes were enormous. More than 150 countries have signed the Global Methane Pledge, a major international agreement aiming to slash methane emissions by at least 30% from 2020 levels by the end of this decade. Meeting this target is critical for slowing global warming in the short term. Yet, as any engineer or strategist will tell you, you can't manage what you can't measure. MethaneSAT was meant to provide the data backbone for this global effort, making transparency and accountability possible on an unprecedented scale. No other satellite blended wide-area surveillance with fine-grained targeting quite like MethaneSAT. Its unique ability to scan entire oil and gas fields, then zero in with a resolution equivalent to just 4 soccer fields, set it apart from its competitors. For Amy Middleton, a key voice at the Environmental Defense Fund, the satellite's promise was clear. This is a setback, not a failure. The value of the data we captured can still drive change. And for researchers at the University of Auckland, who built a state-of-the-art Mission Operations Control Center to help manage MethaneSAT, the project was a matter of national pride. New Zealand alone invested nearly $30 million in the mission, hoping to establish itself as a leader in climate technology. But in June 2025, after just 15 months in orbit, MethaneSAT went silent. The satellite, designed to operate for 5 years and carrying a price tag of up to $134 million, suddenly stopped responding. For the University of Auckland, this meant never even getting the chance to take the controls, a bitter disappointment for a team that had spent years preparing for this moment. For New Zealand, it meant a significant investment drifting away in space, with little to show for it except hard lessons about risk and reward in high-stakes technology. The reaction within the global climate and tech communities has been one of genuine loss. As Stephen Hamburg, chief scientist at the Environmental Defense Fund, put it, "The satellite's failure leaves a gap in the ability to monitor emissions of a potent greenhouse gas. MethaneSAT was developed specifically to identify them." Riley Duran, CEO of Carbon Mapper, echoed this sentiment, warning, "Make no mistake, this is a pretty big gap." Why does this gap matter so deeply? Let's put it into perspective. Methane emissions are not just an abstract environmental concern. They are a concrete, urgent part of the world's climate crisis. Leaks from oil and gas infrastructure, agriculture, and waste management facilities add up to hundreds of millions of tons of methane released every year. Many of these emissions are invisible to the naked eye and undetectable from the ground. Without robust, independent data, even the most well-intentioned companies and governments can underestimate or ignore, the true scale of the problem. Consider the case of so-called super emitters, facilities responsible for disproportionately large leaks. A recent United Nations report found that even when these super emitters are alerted to their methane leaks, many fail to take corrective action. This means that without reliable, transparent data, entire countries could fall short of their climate pledges. The global methane pledge, as ambitious as it is, lacks concrete enforcement mechanisms. Success depends on rigorous monitoring, regular reporting, and above all, accountability. The loss of MethaneSAT throws a wrench into this delicate machinery at precisely the moment when momentum is needed most. So, what happens now that this crucial satellite is lost? Other satellites are still operating, but none offer the same combination of global reach and pinpoint precision. The Canadian company MethaneSAT, for instance, operates a fleet of satellites, recently expanded with C6, C7, and C8, that focus on targeted monitoring of industrial facilities. Their high-resolution spectrometers can spot leaks at individual plants, but they lack the broad, continuous scanning that MethaneSAT provided. Then there's Carbon Mapper, a public-private partnership that uses sophisticated hyperspectral imaging to identify and quantify both methane and carbon dioxide point sources. Carbon Mapper is excellent for mapping out specific emissions across wide areas, but it is still building out its satellite network and relies heavily on aerial surveys and partnerships with other platforms. Meanwhile, TROPOMI, the tropospheric monitoring instrument aboard the European Sentinel-5 precursor satellite, delivers daily global coverage of methane concentrations. However, its spatial resolution is much coarser. It can capture large-scale events, but often misses the smaller, more frequent leaks that add up to a massive climate impact over time. This patchwork of technologies means that, for now, the world's methane monitoring efforts are less coordinated and less comprehensive. The risk is clear. With fewer eyes in the sky, those responsible for the largest leaks could slip under the radar, and data gaps could slow down both policy responses and public pressure for change. As Riley Duran from Carbon Mapper put it, the loss of MethaneSAT, make no mistake, represents a gap in our community's ability to monitor and quantify methane emissions, and it's a pretty big gap. But the consequences go even deeper. Methane emissions are not just a scientific puzzle, they are a political and economic battleground. The Global Methane Pledge, signed by more than 150 nations, aims to cut methane emissions by at least 30% by 2030. Yet, without robust, transparent monitoring, it becomes nearly impossible to know whether countries are truly making progress. The United States, under the Biden administration, has proposed stricter regulations for methane emissions, including mandatory leak detection and repair programs for the oil and gas industry. These regulations hinge on reliable data. So what happens when that data is suddenly harder to get? Let's look at the economics for a moment. The cost of deploying core methane abatement technologies across the globe is estimated at $80 billion. Yet the average cost to reduce emissions by 80% is just $12 per ton of carbon dioxide equivalent. That means, with relatively modest investments, humanity could make huge strides in cutting methane pollution. But again, none of this is possible without knowing where the biggest leaks are, how much is being emitted, and how effective repairs truly are, information that satellites like MethaneSAT were designed to provide. The loss of MethaneSAT also raises profound questions about the fragility of our technological ambitions. Space missions are, by nature, risky. Each launch is a high-wire act, and even the best engineered satellites can fall prey to technical glitches, cosmic radiation, or simple bad luck. As Craig Roger, a Beverly professor of physics at the University of Otago, observed, "Conditions have not been really active, but MethaneSAT seems to be having a bad time for quite a while now. These guys are apparently being repeatedly unlucky, and that's weird." For those who poured their careers into this mission, the emotional toll is real. But this setback also offers a chance for reflection and renewal. Nicholas Rattenberry from the University of Auckland called for a no-blame review to understand how so many warning signs about MethaneSAT's operation were missed. Transparency, both in technology and in management, is essential if future missions are to succeed. Richard Easter from the university's Department of Physics echoed this sentiment, emphasizing that as investors in such projects, countries like New Zealand deserve a full explanation when things go wrong. Looking back, there are historical parallels to MethaneSAT's story. The space age is full of missions that failed, only to spur new waves of innovation. The Hubble Space Telescope, for example, was famously launched with a flawed mirror. For years, it was the butt of jokes, until a daring space shuttle repair mission transformed it into one of the most productive scientific instruments of all time. The lesson? Failure in space is not the end. It is often the beginning of something greater, provided we learn and adapt. So what does the future hold for methane monitoring? In the short term, the loss of MethaneSAT will likely push more responsibility onto the shoulders of alternative technologies. GHGSat's targeted approach will become even more critical for identifying and mitigating super-emitters. Carbon Mapper's ongoing expansion could help fill some of the data gap, especially as more satellites join its constellation. There is also the possibility that the heightened attention to MethaneSAT's failure will accelerate investment and innovation in monitoring technology. Policymakers, industry leaders, and scientists may be more motivated than ever to collaborate and create more robust, resilient networks, perhaps even launching a replacement satellite with improved capabilities and lessons learned from MethaneSAT's demise. In the longer term, this episode may change how the world approaches climate monitoring. Instead of relying on a single expensive satellite, future strategies could emphasize redundancy and diversification, multiple satellites, ground sensors, aerial platforms, and real-time data sharing systems, all working together. This would make the global monitoring infrastructure less vulnerable to single points of failure and more adaptable to changing threats. There are also broader implications for international climate agreements and industry practices. Policymakers may face delays in accessing critical emissions data, potentially hindering efforts to track progress toward emissions reduction targets. But the incident may also spur increased scrutiny and regulation of methane emissions from the oil and gas industry, prompting companies to invest in better leak detection and repair technologies. It may increase pressure on countries to implement stronger enforcement mechanisms for the global methane pledge. Without dedicated satellites like MethaneSAT, there is a real risk of reduced data availability and transparency, potentially weakening efforts to effectively track and mitigate methane emissions. And yet, this crisis is an opportunity in disguise. The urgent need for accurate, timely data could foster unprecedented collaboration between governments, private enterprise, and academia. New partnerships could emerge, blending wide-area scans with precision targeting and leveraging artificial intelligence for real-time analysis. Imagine a world where satellites, drones, and ground sensors form a seamless web of climate monitoring with open data accessible to all. That is the vision MethaneSAT helped inspire, and one we can still pursue, even in its absence. For you, the viewer, what does all this mean? First, it is a powerful reminder of how interconnected our world has become. A malfunction in low Earth orbit can ripple through climate policy, industrial practices, and even the quality of the air we breathe. It highlights the importance of technological redundancy, the need to avoid putting all our eggs in one basket. It also underscores the power of transparency. The more open and robust our data, the harder it is for polluters to hide their actions and for industries to shirk responsibility. Practically speaking, this is a call to stay engaged and informed. Over the next few years, policy and investment decisions will shape our planet's climate for generations. Understanding the tools we have and the gaps they leave empowers us to demand better from corporations and governments alike. For those working in the tech and science fields, the need for creative solutions has never been greater. Methane emissions can be reduced by 80% at an average cost of just $12 per ton of carbon dioxide equivalent. The technology already exists. What's missing is not the know-how, it's the will to act, and that starts with reliable, accessible information. Can existing or future technologies fill the void left by MethaneSAT? For now, the answer is both yes and no. While GHGSat, TRPOMI, and Carbon Mapper each bring valuable capabilities to the table, none perfectly replicate the unique blend of coverage and precision MethaneSAT offered. The path forward depends on rapid innovation, greater international cooperation, and a willingness to learn from failure. MethaneSAT may be gone, but its brief mission has already changed the conversation around climate transparency and accountability. And here's a truth the public rarely hears. Many of the world's largest methane leaks remain undiscovered simply because no one is looking at the right place at the right time. Until monitoring is as constant and ubiquitous as the emissions themselves, true climate accountability will remain just out of reach. That is why every lost satellite, every lesson learned, every new partnership matters, a reminder that the fight against climate change is as much about persistence as it is about innovation. If you found this video eye-opening, share it with someone who cares about our planet's future. Subscribe for more insights on the intersection of global economics, technology, and the environment. Let's keep watching the skies and holding each other accountable. Because in the end, the fate of our climate is not just written in